we were able to solve real-world challenges in areas of reliability, scalability, performance. Of course, there's also always trade-offs with these areas and also drawbacks. But today I want to show you how we managed to tackle these reliability and scalability concerns and all the lessons that we learned along the way. So let's dive in. My name is Natan Silnitsky, and I'm a backend infrastructure tech lead at Wix. And for the last 8 years, I've been developing tools and frameworks all around specific areas. Started with CI/CD, moved to a lot of years with Kafka, and more recently with the microservices frameworks. I also gave talks in numerous tech conferences around the world, and also wrote a lot of blog posts on these subject matters. And other than that, I'm a big yoga and fitness enthusiast. So for those of you who don't know, Wix is a powerful website building platform that allows you to manage your online presence, but also manage your business online. And we were the pioneers of using AI already 10 years ago. And with the Wix platform, you can use sophisticated tools like third-party drop shipping, all the way to managing your bookings and schedule for the yoga studio. Our goal is to allow any size business, could be a tiny business or huge business, utilize all the benefits they can get from the Wix platform. So before we moved more towards Kafka, most of our communication style and architecture was around synchronous models. And this could work quite nicely for small scope and not so high scale. But as complexity grows, as you get a lot more microservices, this kind of paradigm falls down. You get more bottlenecks, increased latency. For example, with this e-commerce flow at Wix, the checkout service, it needs to fetch information for many different microservices, including price from catalog, is it available from inventory, does it have a ribbon, etc. So all these fetches can incur a lot of delay. And all this delay will definitely impact the user experience of the shopper at the end, and the overall system performance, right? Also, in addition to read flows, you also have write flows that are not really critical to the checkout flow, like creating invoices or sending out emails. So if you do that synchronously during your flow, that also incurs a lot of delays, and it will slow down the entire checkout flow. Also, it's missing fault tolerance built in here. You can do some ad hoc changes, but it's not bulletproof. So with this kind of synchronous model, you get a system that is more fragile and has a lot more potential failure points. Now, this is more like Wix has its system today with the asynchronous model. And Kafka is really at the heart of this model, where all the checkout flow is very decoupled among the services. You still get some RPC at the edges. And you may be wondering, wait, the checkout service depends on inventory service and ribbon service to get data it requires quickly so the shopper can continue checkout. So how is that done asynchronously? So I will show a bit later that as well. We also get fault tolerance here with Kafka, consumer retries out of the box. And you may get delayed processing, but that's better than RPC's cascading failures in the synchronous model. So to demonstrate Kafka's benefits and versatility, I will share 4 key asynchronous patterns that are widely used at Wix, and they are used in something like already 4,000 microservices that are mostly written with our internal backend platform called Nile. So these patterns are implemented in Nile, and they solve real-world challenges with Kafka. So I'll show you when, why, and how to use integration events, a task queue, a task scheduler, and an iterator. So hopefully by the end of this, you will fully understand the design and all the trade-offs that are quite interesting for these patterns. Okay, so let's start with our first one, integration events, which really is the backbone for decoupling microservices ecosystem, especially as like Wix, you have thousands of microservices. So integration events promote event-driven interactions. They reduce the dependencies between the services as each one acts completely autonomy. So instead of having synchronous flow, we utilize Kafka producers and consumers, and all the services act independently, only aware of the message broker. For example, the order service, it emits automatically these integration events for created, updated, and deleted situations. And it doesn't know anything about the consumers here. So it gives us a lot of flexibility, a lot easier scalability and fault tolerance, because it's a much more modular, resilient architecture. And I'll touch on that a bit later on as well. But another very crucial aspect of integration events is that they allow us to get query optimization. So let's see how that's possible. If we look at synchronous style here, like I mentioned before, you get a lot of latency when you do all these reads from different API services. And we are really slowing the response to the user. So how can we improve it slightly? Well, the services can move to read replicas databases. So for each service, the call will be faster, but we still get a lot of network calls here. So maybe introduce a cache, right? That's a popular optimization. But when you have ever-growing scale, caches help only up to a point for the bulk of the requests, but there could be a considerable amount of requests that have cache misses, and again, a slow response. So another solution is needed to ensure a low latency. With integration events, we enable seamlessly prefetching reference entities directly into the main entity. So for example, here we have the catalog service, and it has the product entity, the main entity it handles. So all it needs to do is listen to inventory service events and enrich the product information with the data from inventory. And with this information, like Kafka has been used for many years at Wix. We had a lot of producers and consumers in the past. But what's different with the concept of integration events is how it really simplifies moving seamlessly to asynchronous model. Because every Wix service is built on the Nile platform, it gets the data layer out of the box, and the data layer automatically sends out these integration events on each database change. So it really boosts the API performance, because utilizing these events, we can prefetch data by other consumers to reduce the response times. So how does these integration events look like with our definition language, with protobuf? So the inventory service will have the inventory item, and it is includes all the necessary fields in its domain, including quantity. And this is the special part, the custom part. And then we have the standard part, definition in protobuf, the payload, and it includes the body. It will include also which type of event is it, created, updated, etc. And importantly, the entity sequence number, in order to make sure that the events are handled in order. Another important aspect here is to automatically generate the Kafka topics, so that won't bother us either. So the main entities have a unique identifier that we are sure is unique across the system, so we can safely create the Kafka topic for each integration event for each entity. And now all that the catalog service is left to do is it has the product entity defined, and part of it is the inventory details that it doesn't own explicitly. But in the background, it can listen to inventory service events and enrich this data while consuming from Kafka. And now our catalog service doesn't only consume data from inventory, it can also consume data from ribbons or other services in order to make the complete picture of the product entity work. And that means that we now have the checkout service that doesn't need to interact with all the different services related to managing the catalog. It only needs to send a synchronous request over to the catalog service, which will have all the information available. Now, beyond integrating between different Wix services, integration events also has other additional benefits. They can automatically feed the data warehouse or data lake because of this standardized schema between all the services. It's really simple to ingest it. It can also feed the search engine to index it, or the AI vector data for a RAG to feed that as well. And also because Wix platform has a lot of external developers, it's really easy now to translate these webhooks to, these Kafka events to webhooks or JavaScript callbacks, so they can utilize it on their end, the external developers. Okay, so I showed you how great it is, but there are a few drawbacks for doing automatic integration events. First, you incur waste because you do heavy produce, because each database change is heavily produced around the system. But sometimes you won't get any consumers, right? So how we mitigate it? We start off with just one Kafka partition, and we increase it if consumers are actually needed. And we get, on the consumer side, header-based filtering. So the consumers will not deserialize the entire payload. They will only do that if they actually care about this type of event. The second thing here is consumer lags, of course. So we get eventual consistency in our design. That's especially painful for read your own write flows, as the shopper, for instance, expects to get instant feedback. Not the shopper, sorry, I mean the store owner, because let's say they manage their back office and they want to update some product information. They want to know exactly that immediate feedback that the product was changed. So if you're working with eventual consistency here with consumer lags, then you're going to change your UI design probably and create a refresh button or something like that. And lastly, we also get harder investigations for data corruption, which are more challenging to detect. So in this case, we're trying to mitigate this in advance with the sequence numbers I mentioned earlier, to get proper in order. And also idempotency. So we want to make sure that even if the same event is processed multiple times, the side effect will only happen once, right, during consumer retries. So to summarize, the integration events really help us with decoupling our distributed system, as we can independently have event-driven interactions between the services as our scale grows. And also it boosts query optimization as we prefetch the data, so we reduce latency. But there are the drawbacks I mentioned, resource waste, so we try to do selective processing and deserializing. And we mitigate eventual consistency with reliable retries, idempotency, and we also change the UI design in order to accommodate for it. Cool, so let's jump over to the second pattern out of 4, our task queue. So this pattern allows to offload non-critical tasks, like sending the emails from the main workflow. This streamlines the request and keeps the critical flow much faster. So like I mentioned before, we don't want to have this create invoice, send emails part of the main flow, because it's not part of the critical flow. But this, like I mentioned, can incur slowness, bottlenecks, fragility with errors handling, etc. So this is what we do instead. We submit this task to a task queue. It's a very simple pattern, but if you think about it, it's very powerful because it will improve the response time quite a lot. You can think of it as running a thread in the background, but unlike a thread in the background, it utilizes Kafka. So it's much more robust. You get the async queue experience, and it can handle high volume and easily handle any type of failure. So we're trying to simplify running this concept instead of producers consumers. So you create a task queue, specify the Kafka topic and the handler, and then the consumer executes the handler, and we get automatic retries, of course, very important. And when you submit the task to the queue, it actually means that there's a Kafka producer behind the scene that produces the message. So now, with this task queue concept, the checkout handles all these tasks in the background, and it's resilient, and the synchronous flow works much faster. In terms of drawbacks here, so monitoring the situation is harder than the synchronous model, of course. What can we make sure that the side effects actually happen? So how to mitigate this eventual side effect happening? So we employ more tracing technologies, make sure that the request ID is propagated throughout this flows within our logs, within our traces and spans. We use OpenTelemetry format. There are other formats as well, of course. Very important to keep tabs on what's going on behind the scenes. Again, here there's also the risk of consumer lags. You cannot avoid that with Kafka. So this, of course, is mitigated with lag alerts, auto-scaling the partitions, auto-scaling the pods. It's a manual operation to increase partitions, but Kafka has a new feature in preview mode called a share group, which may help us avoid needing to manually increase partitions because multiple consumers can work on the same partition. So hopefully we'll be able to utilize that in the future. And the task queue pattern will not work as optimally if you get like a sequence, a pipeline of tasks that you need to perform in the background. For Wix, this is not usually a concern because we're trying to fragment our business to as many smaller components as possible for the flexibility and pluggability. So usually one service will not incur a long pipeline, but there still are some use cases for that, and I will discuss how to mitigate that later on. So to summarize task queue, it decouples background work, so it allows you to synchronize requests, but all the non-critical tasks run in the background. It improves response time, but there is the drawback of harder monitoring, so it's important to put the tracing tech in there to make a reliable production environment. Cool, so we have our third pattern out of 4, the task scheduler. So this one enables precise, fault-tolerant, delayed recurring jobs. So basically we're talking about robust scheduling capabilities. Why do we need such things? For example, in e-commerce solution, when a shopper checks out, the checkout service will want to schedule a future task to check that either the checkout flow was completed, or if not, it will send out an email, hey, maybe you want to finish your purchase, right? It could mean a lot of money, these notifications. So one approach to doing this is to utilize the Kafka consumer and just sleep when you want to delay the task. But there are scalability issues in such approach. You get higher latencies and potential bottlenecks with all these sleep operations. So that's, and another thing is inefficient resource usage, because the threads are idle when they sleep, unless you're using virtual threads if you're on more recent versions of Java. And here we can see, like, if you put delay of 15 minutes waiting for any longer delay on a single partition, you will have a problem, because the 60 minutes delay will happen first, and then instead of 50 minutes delay, you get 60 minutes delay. And that can really hurt sale potential because the shopper has moved on to a competitor. So instead, we want to utilize a proper scheduler service that will store the tasks in a database. So it eliminates the sequential processing with Kafka partitions. And of course, it will give us more scalability and flexibility. So how does this flow work? We're going to insert the task to the database once it's submitted. And each minute, we're polling for eligible tasks to schedule, to trigger. Now, it's important for scalability for the scheduler service to have multiple shards, each one polling and looking at its part of the database. Otherwise, we won't have a good performance and a scalable solution. And then after the designated time passes, we can utilize the Kafka producer as the task was activated and produce the Kafka to Kafka for processing. So now the checkout service processes the scheduled task, and it can send out the email. And because we're using Kafka Consumer, we will get the ability to retry out of the box. So this ensures a reliable flow where eventually the scheduled task will be processed correctly. Now, there are some drawbacks to this implementation. We sometimes see increased database load and some scaling issues. So even with our applicative sharding, so we're thinking about also splitting up the database to multiple shards. And because of Kafka's at least once guarantee, so we want to make sure that there is processing. That means we get duplicate processing sometimes. So these kinds of patterns always go hand in hand with the idempotency tools I mentioned before. And with this polling that is done on the database, you may get a trigger lag. At Wix, we experience sometimes 15 seconds, and in the worst case, we saw 1 minute. But for 99% of use cases at Wix, it's totally fine because we are scheduling something in the future. It doesn't matter if it happens a few seconds later, but we are considering improving it for the future with the database sharding. Now, at Wix, we have created our own Kafka-based task scheduler implementation, but of course, there are open source alternatives out there. We have the Quartz and Job Runner. So Quartz is more a legacy solution. It's more centralized and it has scalability limitation. Job Runner is a lot more modern, but the open source version limits you to 100 concurrent jobs. So if you want more, you're going to have to pay for the managed solution. So to summarize the task scheduler, you get reliable delayed tasks with automatic retries. So I think we can avoid using thread sleep from now on. And yeah, our task scheduler also provides a test kit for the Wix developers, which is kind of nice because it's tricky to incorporate in your integration tests the idea that a task is scheduled in the future, so you can play around. Don't need to play around with clocks and stuff like that. And there's also the duplicate scheduling because of the at least once guarantee. So definitely need to deploy the idempotency guarantees, either with dedicated database that handles idempotency issues and make sure that it's only the processing only happens once. Okay, so we reached our last pattern for today, the iterator. So this pattern is for long-running jobs. The idea here is to process very big workloads in much smaller chunks. That gives us scalability and resilience, even for very high demanding, time-consuming tasks. So for example, when is that needed? We have the Wix store's back office, so the store owner wants to update all the ribbons in bulk. Let's say they have a ton of products they inserted in the last couple of days, and they want to update that they are on sale now. So here, it's really important to ensure that we have accurate updates, and we do want to do the updates seamlessly across a lot of listings. So it's important to maintain consistency. And the bulk update requires a long-running job, right? Especially like there are stores in Wix with tens of thousands, hundreds of thousands of catalog items. Okay, so one approach may be to do a SQL statement of update these products with the on sale ribbon where they were created in the last 48 hours. Okay, that's nice. That will only work for a relatively small batch of products. And we don't know how many of them there will be in advance. So we may fail the transaction if the number is bigger than expected. So we need a more scalable solution. So we can process doing this bulk update page by page, and we'll apply the ribbon in bulk only to a single page returned from the database. But this, of course, is time consuming. So again, we won't want to do this synchronously in our flow. We will want to do it asynchronously to prevent blocking anything else. And by the way, parallelization might seem like a nice optimization here, but it could mess up our page-by-page processing. So we don't allow parallelization currently in our iterator pattern. Maybe we can use the task queue we talked about earlier. So we'll do a quick submit and return the response quickly to the user. That sounds good. And then we'll process the asynchronous task in the background. That means that the Kafka consumer will query database page by page and do the update of the ribbons until it completes. So, seems like we're good to go, right? But actually, in distributed systems, there could always be errors. You always want to think about what could go wrong, right? So here, we have a single message that is processed by the Kafka consumer. Any error means that it will need to retry and start all over again from the beginning. So that really slows us down. And it doesn't only waste precious resources and processing time, it will also slow down consumer scaling and consumer rebalancing because you don't want to interrupt this and move the partitions to another consumer. So definitely harming the overall performance with the long-running jobs. So instead, we can utilize the iterator pattern. So with the iterator pattern, we use Kafka and we split the job into smaller jobs integrated into the Kafka produce consume cycle. So each time we will produce the next page to consume and process, and each of these pages are consumed completely independently with the Kafka consumer. And this way we limit the blast radius of any error that we only to a single page, right? So the retries will only be on a very small subset of the data set. So this keeps processing short and doesn't impact the consumer rebalancing or auto-scaling or anything like that. It keeps things running smoothly. And also, you don't have to only work with the database in such a pattern. You can also process any iterable job that has paged data source that provides the data page after page. For example, you can use the inventory service to utilize it and update, get updates from it, so you can update the catalog service page after page. So here we can see a quick example of what does the iterator pattern looks with the pseudocode. We have here the handler for the iterator. This is a distributed iterator, right? So we first fetch the product by filter, and then we want all the products in this page to be updated in bulk, hopefully, right, with the database SQL statement or something like that, because doing it one by one will really slow us down. And finally, we want to return to the iterator how to proceed, what will be the next page to form, to process for until it completes. And also, in addition, the iterator library integrates the job service with a job service to track the progress. So now a client can monitor the status of the job via API, and it will be in progress until all the pages are done, and then the status of the job will turn to done. Okay, so it looks quite helpful and resilient. Some drawbacks here. Again, we require to have strict idempotency because of the Kafka consumer. We need to make sure that we don't do duplicate work and mess up the data. And this pattern actually employs Kafka with produce, consume. That does incur additional overhead and latency. But because we're talking about a background bulk task, it is expected to take a longer time. So this overhead is not significant versus the entire bulk operation. So to summarize, we get a simplified data traversal pattern with a unified way to loop through big data sets. And because it's fault tolerant, because it only works in a single page of data at a time, so it really reduces the blast radius. On the flip side, we do have some performance impact with this Kafka produce consume overhead, but usually it's not that important. Now, I talked about all these patterns on the sense of how to utilize Kafka or other message brokers. Definitely, like you saw, definitely a relevant option. Another one is workflow engines that can also do the trick. One example is temporal that can actually, it also has internal queues like Kafka-like hidden behind the scenes to manage all these workflows and tasks. It also keeps the state in database in order to make sure that if there's some error, then it will know exactly where to pick off. So that ensures fault tolerance. And I don't have scope to do a deep dive on temporal, but I did give a talk on this subject of deep comparison between Kafka and temporal, between workflow engines and event streaming brokers. So you can check that out, and I will share the link to the slides in the end. So you don't only need to remember one link. Okay, future plans for Wix. So the Wix platform, like I mentioned, is modular. We have an emphasis on small microservices, usually working on a single entity. All this entity manipulation is available through APIs, SPIs, and of course, events, like integration events. So this offers flexibility and pluggability for external developers as well as internal Wix developers. So it's a lot easier to integrate with. But sometimes the service will want to get a small set of tasks to perform sequentially. So we are considering introducing a task pipeline pattern, which of course is easily implemented in a workflow engine, but can also be done straightforwardly with Kafka. But we are cautious about this area because if we start moving to a full-blown orchestration with an orchestration manager, we undermine the flexibility of our event-driven choreography, and it will be less pluggable. And the mindset will be more about let's put another thing into the pipeline and not how we make sure that everything is available for external developers. Other than that, we also are considering adding a polling pattern because sometimes you want to wait for third parties to finish something and change the status. So you keep polling it for the result. So instead of doing direct task scheduler and loop there, we just offer an even higher level abstraction of a polling pattern. So this slide here just summarizes everything quite nicely in a single place, where you can ask yourself which pattern to use when. So if I want to avoid high latency on reads, then I can utilize integration events. Or if I want to decouple non-critical write tasks, then we're using task queue pattern. And of course, when to use this task scheduler or the iterator pattern accordingly for all the different types of use cases. Like I said, I will share the link at the end. So to summarize, today we explored Wix's journey from synchronous request supply structures to event-driven Kafka-powered asynchronous patterns. So these removed a lot of bottlenecks, reduced latency in our distributed system, improved scalability and fault tolerance by a long measure. So I hope I shared a lot of practical lessons from our real-world challenges today and how to mitigate them. And I actually gave talks on more event-driven patterns and asynchronous patterns in the past. So you can check out that as well. Like I mentioned, you just need to remember one link here. The link is slideshare.net/Natan Silnitsky. I will also share everything on social with the LinkedIn and on X and on Blue Sky and on my website. So you have many different options to get these slides. And I want to thank you very much.